Welcome to our 7th morning workshop over thermochemistry. We started a little bit here, and we're going to just jump right into problem number 1. It says, in a thermodynamic study, a scientist focuses on the properties of a solution in an apparatus as illustrated below. A solution is continuously flowing into the apparatus at the top and out at the bottom. Such the amount of solution in the apparatus is constant with time. Is this solution in the apparatus a closed system? What do you think?
I'm not inclined to believe so since it's open. I think heat could just escape the system.
Yes.
Exactly. Whenever we do thermochemistry or whenever we do any sort of scientific experiment, we really want to make sure that we're dealing with a closed system. And the reason why we do is because if the system is open, if there is transfer into and out of the system, we can't isolate the variables and we can't determine what is in fact happening. Like if it's the result of things that we do to the system or if it's something from the outside. So whenever we are dealing with this type, whenever we're dealing with these types of problems, we always want to look at is the system a closed system? And a closed system, like I said, it does not allow for anything to come in, and it does not allow for anything to go out, except perhaps for energy. Okay, so the energy can be transferred to the surroundings, or it can be transferred to the system. But essentially, we want the system to be effectively closed so that at least no material gets transferred in or out. And this is clearly not the case here. So it says, if it is not a closed system, what could be done to make it a closed system? What do you think?
Put it in a box.
Put it in a box.
That's if it's I mean, if the box is an insulator, I guess that would work. But there's even a simpler way to do it.
Well, also the problem with the box, it doesn't change the fact that solution's coming in and solution's going out. What could we do to make sure that this is a closed system? Any idea?
I guess just ensure that. I don't know. I was thinking make sure that nothing comes in and nothing comes out, but then you might not have a reaction. So.
Yes, you have the right idea. So we can plug the in valve and we can plug the out valve. And what about the top?
Just put a lid or something on it, like a plate, maybe. I don't know.
Yep. Seal the top.
Yes.
But another thing that we could do, if we need the flow of liquid, if we needed the flow of solution to occur for the purposes of whatever we're studying, we could connect the in valve to the out valve so that the solution is continuously flowing in a circle.
What a concept. Interesting. Yes. Yes. Nice.
Okay, cool. So let's look at some simple applications of this equation that we mentioned up here, that the change in internal energy is equal to the Q plus the W. All right, so it says for the following process, calculate the change in internal energy of the system and determine whether it's endothermic or exothermic. Now, as Dr. Neely mentioned, that endothermic and exothermic do not describe changes in energy. That would be endergonic and exergonic. What endothermic and exothermic refer to specifically is only the Q. Is heat being absorbed or is heat being released?
Yes.
Okay, so let's look at this. For A, it says a balloon is heated by adding 900 joules of heat. It expands, doing 422 joules of work on the atmosphere. So if we consider the balloon a closed system in that there is no air going in or out of the balloon is tied off, it's isolated from its surroundings, right? So we add 900 joules of heat to the balloon. what is the value of Q for that balloon? What is the value of Q for that balloon system?
Or before we determine the value of Q, um, um, what is the law? What law should we, yeah, what law should we think about? What is the name of this law that Professor DePaul just wrote?
Conservation of energy.
Yeah, the law of
Thank
conservation of energy. Exactly. This is an expression of the law of conservation of energy. Very good. So what would the value of Q be in this case? Would we consider this a positive Q or a negative Q, first of all?
Positive, because you're adding the heat into the system.
Exactly. You're adding the heat to the system. So the value of Q would be positive what?
900.
Positive 900. Very good.
Yes.
Now what about the work? What would be the value of W?
Negative 900, right? Since it's trying to go to equilibrium.
Well, no, the
Or
work is not negative 900.
Oh, I'm
900
sorry.
only refers to the heat.
Is it 422 joules? Oh no,
Positive or negative?
losing.
so is it a plus 422 or a minus 422?
Yeah, is this 422 a positive or negative?
It should be negative because if you're doing work, well, actually, I don't know.
Well, you said negative because you said negative because you're doing work on what?
Doing mm, on the
Is the work
atmosphere.
you're doing work on the atmosphere, exactly. And the
Yes,
atmosphere is the surroundings, is it not?
yes.
Yes.
If the balloon is pushing out on the surroundings, is it if the balloon has to push out on the surroundings, is the balloon spending energy or is it gaining energy?
Spending.
Spending.
Yes.
It's spending, exactly. Like think about yourself. If you have to push out on something, let's say you are inside the balloon. If you have to push out on that balloon, you're spending energy pushing out. However, if the atmosphere, the surroundings is pushing in on you, then you don't have to do anything. You can let it push in. And in fact, because air has a certain sort of elastic quality to it, so to speak, and it can be compressed and expanded, right? If air is compressed, that adds energy to the air because those air particles are moving fast and they're hitting the walls of the container. They have an increased pressure, and so that has an increased amount of energy that's packed into that compressed air. And that when that energy is released, it pushes outwards. So yeah, if the
And you may
system
remember,
pushes out, it's a negative. It's a loss of energy. It has to spend energy to push out. But if it's compressed, that's adding energy to the system.
yes, and you may recall from physics, according to the definition of work, work is the energy used to cause an object to move against a force. And there's a relationship for that. Work is equal to force times displacement. So whatever Professor DePaul described in words, I just put it in an equation. And yes, it is plus delta E is equal to plus 478 joules. That's correct. Is that endothermic or exothermic process?
For number 3?
Yeah, for part A, yeah.
Oh, sorry, my bad. I was looking at the wrong thing.
No problem.
It should be endothermic because you're adding 900 joules of heat.
Yeah, the system is absorbing energy here, so that is definitely an endothermic process.
Yes.
Endothermic. Ah, I'm sloppy in my writing, forgive me. So now, what about B? The 50-gram sample of water is cooled from 30 degrees to 15 degrees, losing approximately 3,140 joules of heat. What is the value of Q for this particular problem?
How do we determine Q? What is the relationship between Q and mass, specific heat, and change of temperature?
Well, in this case, there is a relationship there, but the truth is we don't actually really care about it at this point. Um, and that's, we don't, reason we don't care is because our focus is really not on specific heat or anything like that. Our focus is only on the Q and the W. And it already talks about the heat, right? So what would the
Yeah,
value of Q be here?
It should be negative 3140 joules.
Why do you say negative?
Because they're losing a certain number of joules.
Uh-huh. And what about the work?
yeah, except that I mean, you're right that, we really don't need to calculate, we don't need to calculate the Q, but if we actually do, out of too much curiosity, if we do calculate the Q value, it turns out to be minus 209 joules and not 3,140 joules.
Yeah, it's interesting. In this case, it would seem that there is something fishy going on.
Yeah, so, but I mean, we don't need the numerical value, but it's off by several factors, because if we take 50 grams and multiply it by the specific heat capacity of water, 4.18, and multiply that by delta T, which is 15 Kelvin, that result is 209. And
Yep.
then we'll just give it minus, because so we can just change this number 3140 joules to 209 joules, and then everything will be good.
Okay. I will uh, I will change the number because you're right. And that is the more accurate number. So there you go. Negative 209. Now, what is it? What about the work? What is the work going to be for this particular process? Is there any work for this process?
You wouldn't expect there to be work since you're removing heat. I wouldn't expect there to be work.
Exactly.
Well, technically speaking, there could be work, but in this case, no work is mentioned. So you can assume in this case there would just be 0. And there we go. I think do y'all feel pretty good about this concept of heat and work? Now, is this
I'm okay.
exothermic or endothermic? What do you think?
Exothermic.
Definitely exothermic because it's a negative value of Q. Exothermic. All right, cool. Now we could do C, but I don't know if we really need to. What do you think? Should we go ahead and skip that one?
Yes.
Okay. Any questions on this concept of internal energy and heat and work?
Not yet.
I'm sorry, did somebody say yes or no?
Oh, I said not yet.
Okay. Okay. All right. So now let's take a look at the reaction here. It says consider the following reaction. Methanol reacts to form carbon monoxide and hydrogen gas. So CH3OH reacts to form CO and 2H2. The delta H of this reaction is 90.7 kilojoules. It says, is heat absorbed or evolved in the course of this reaction? Evolved is just a fancy way of saying released. So is heat absorbed or released in the course of this reaction?
Absorbed.
Yeah, heat is absorbed. You can tell because it has a positive value of delta H. Now, actually, before we even delve into the delta H, I should clarify something real quickly with you, and that is this. If we, sorry, my son, uh, my son's very sweet. He has autism, but he loves more than anything to go into the bathroom and shake toilet paper. That's why my wife had to take him out.
Aw.
All right, so so here's the deal. Basically, um, when we're considering enthalpy is both Q and W are what you might call path functions. The value of Q and the value of W depend upon the path taken. Now, to kind of explain what I mean by path function versus state function, a state function is determined only by the current state of the substance. It doesn't matter where it came from. It doesn't matter where it's going. It only matters, what it's doing right now. What is its state right now? So an example of a state function would be temperature. It doesn't matter what the temperature was earlier. It doesn't matter what the temperature is going to be tomorrow. The current temperature is the temperature. It's only dependent upon the current state. Yesterday's temperature has no effect on what today's temperature is. You know what I'm saying? Like, I mean, technically speaking, yes, we know that there's like clouds and other things like that. But the temperature of something is only dependent upon its current state. Does that make sense?
Yeah.
However,
So question, what about pressure? Is that a state function or not?
Dependent.
oh shoot, I
sorry, I
actually have
couldn't.
to confess, I'm not entirely sure myself, but I'm thinking it is a state function.
State function.
Just like temperature, pressure and volume are path independent. It doesn't matter how you got there. It's just the final state that that they're in. So temperature, pressure, volume, they're they're they are they are they are okay. So temperature, pressure, volume, they are state functions. What about location? That's a state function. What about internal energy? That's a state function. But Q, heat, and W, work, are not state functions. Does
Yeah,
that make sense?
they depend upon the path that you take. For example, if I um, if I were to say um, the best analogy that I can think of to help you understand state function versus path function is the idea of displacement. Okay, so for displacement, that's the distance from where you start to from where you end. Okay, so that's displacement, where final position minus the initial position. So if I moved from this chair to the kitchen, um, I would have a certain displacement, right? But if I got up from this chair, went to the airport, flew around the world, came back, and then went to the kitchen, the displacement would be the same. I would still have moved from the chair to the kitchen. but the path that I took to get there would be very different. Okay? So it's a state function, doesn't matter. Displacement is a state function. It only depends on the initial state and the final state. It only depends on the state. So, however, a path function depends on the path. So for path would be like, for example, how much money I spent to move from here to there. And so likewise, Q is how much heat was transferred in the process of changing the internal energy. That depends on the path. Or work, how much work was done in the process of changing the internal energy. That depends on the path. So these things are path functions because they depend on the path you take. Just like distance, the distance that I traveled in going all the way around the world and then going to the kitchen is a very large amount of distance, a very different distance than going from my chair to the kitchen. So displacement and distance are similar in the sense they describe a certain length, but one is a path function. Displacement is a path function describing only the change in my initial to final position, whereas distance actually refers to all the actual movement that I performed. Does that make sense?
And for brevity, we can just define state function as a function of property whose value depends only on the present state or condition of the system, and and um, and it does not depend on the path used to get to that state. It's kind of it's a very basic definition in thermochemistry and thermodynamics. So I think it's important to understand which parameters are state functions and which aren't, just based on this path dependent or path independent definition.
So the reason why we don't really we chemists wanted a way to describe the transfer of heat in a way that was not dependent upon the path. In other words, we did not want to have to deal with the path function properties of Q. So we wanted to make it a state function. So they developed this concept of entropy, which is basically you can think of it as Q plus P times V. Okay. Now, essentially, when we take the derivative of that, we get the delta H, we get the change in enthalpy is equal to the Q plus the pressure times the change in the volume plus the volume times the change in pressure. Okay? Well, now here's the interesting thing. Sorry, I apologize. Let me fix this. I made a mistake. It's not Q plus PV, it is energy plus PV. Okay? And there's a reason, there's a method to my madness here. Suspension of disbelief. Hold on just a moment. Okay. Delta E is equal to P delta B and then B delta P. It's kind of how we have to deal with these complex derivations in calculus. Okay? And we're not going to go through the whole calculus, but I wanted to show you something interesting here. See, the pressure times the change in the volume, when you talk about work is equal. Remember how we said work done on the system? We said work done on the system is positive when the system is compressed. That means a compressed system is a negative change in volume. And so a negative change in volume, if I want a positive work, I have to add another negative sign. And so pressure, volume, work for the system, the work of the system, when it's positive, that means energy is added to the system by means of work. And so a change in volume, let's say, for example, you went from 4 liters to 2 liters. If the system was compressed from 4 liters to 2 liters, then we would say the delta V would be the final volume, which is 2, minus the initial volume, which is 4. And so the delta V of that compression would be negative 2 liters. So anytime work is done on the system, delta V is negative. In other words, anytime you add energy to the system by means of pressure volume work, the delta V, the change in volume, is negative. Does that make sense?
And really, this mathematics is interesting, but the big concept is to understand what enthalpy is. And enthalpy is very simply the heat absorbed or heat released under constant pressure. So here's a question for you guys.
I just want to make sure that this is clearly understood, though. Also, forgive me for one moment. So does it make sense why the delta V has to be negative for the work of the system to be positive from your perspective?
I think it makes sense to me. It's going to take a little bit for it to really sink in, but I think it does make sense.
And admittedly, I am going a little bit down the rabbit hole, but I promise I won't go too deep. But essentially, okay, so the reason, so that I wanted to emphasize, that is why you must have this negative in front, because the delta V is always going to be negative if the work on the system is positive, because it's always going to have a negative delta V, and therefore adding work to the system is going to require that the work of the system is positive. The only way it's positive is by adding another negative there. This is why this is important. When I take this derivation here, the delta H is equal to delta E. Well, I know delta E is equal to Q plus W, right? Which plus pressure times change in volume plus volume times change in pressure. Now, if I substitute that negative P delta V for the work, I see that the delta H, the enthalpy, the change in enthalpy, is actually Q minus P delta V plus P delta V plus V times delta P. Well, one thing you might notice is that the P delta V and the P delta V here cancel out. So it doesn't matter if the volume changes, because those two effects cancel each other out. So the delta H is basically equal to the heat transferred plus the volume times the change in pressure. And this goes back now to what Dr. Neely was saying, is that if the pressure is constant, what's the change in pressure? What's the value of this? What's the value of this delta P? If the pressure is constant, what's the change in pressure?
0.
0, exactly. And so since the change in pressure is 0 because it's constant pressure, there is no change in pressure. That negates this last piece, and chemists now have delta H is equal to Q as long as the system is at constant pressure. So what we did by this is we discovered that enthalpy, this state function, is basically equal to Q as long as the system is under constant pressure. And that's going to, so from this point forward, as far as you're concerned, just to keep things simple, we're going to use delta H and Q interchangeably, okay? Q and delta H are going to be used interchangeably because we are always going to assume, at least we're almost always going to assume, constant pressure.
Thank you for the.
My explanation was that it might be not necessary. I thought it might be helpful because sometimes professors do want you to know some of this stuff, particularly like so the system is negative P delta V. But anyway, I hope that didn't create more questions than it answered.
Well, I have a question.
Okay.
So, based on this conceptual proof, is delta H, is it heat flow or is it not heat flow?
It's
Here's,
heat flow
I can
plus
tell you.
benefits.
Yeah.
It's a heat flow plus bonuses.
Yeah. So,
It includes that volume times change in pressure component.
yes.
Essentially, it's a measure of the energy, strictly speaking, and we can't ever really measure isolated enthalpy, but we could call it enthalpy in and of itself, not change in enthalpy, but enthalpy itself is a combination of the energy and the pressure times the volume of a system.
But you're right, we cannot measure enthalpy of a system, but we can measure the change in enthalpy designated
Yes,
as delta H. And
exactly.
um, and really the point that you've arrived at is very important, and I'm going to cement it in. Delta H is not heat flow. It is like heat flow. There are two differences between Q and delta H. For one thing, delta H is a state function and Q isn't.
Hmm.
And the second important difference is that delta H is heat flow under constant pressure, whereas Q is heat flow under any condition. There you
Yep,
go.
that's true. Very good. No, that's a very good point. Thank you. All right, so in
Thank
this case, now that we've basically a very long way around because of me uh, established that delta H and Q are going to be effectively equivalent for most of our purposes as long as we assume constant pressure. Though we know they're not the same in all circumstances, and under constant pressure they're effectively equivalent. So now we're going to, and delta H was negative, it's an exothermic. If it's positive, it's endothermic. This is clearly an endothermic reaction, and as Ethan mentioned, that means heat is absorbed. So heat is absorbed in this case. Now,
yes.
just calculate the amount of energy when 45 grams of CH3OH is decomposed by this reaction at constant pressure. Notice the use of at constant pressure. At constant pressure means that this is a valid assumption. Okay, so here's the deal. When we're given an equation like this, and this is actually a really, really important part, so I really want you to pay attention closely to what I'm about to say. When we're given an equation like this, and we're given a corresponding delta H, what this basically tells us is that for the molar amounts indicated in this reaction, in other words, if for 1 mole of methanol, CH3OH, reacting and breaking down into 1 mole of carbon monoxide and 2 moles of H2, that the delta H is going to be 90.7 kilojoules. In other words, in order to cause 1 mole of methanol to break down into carbon monoxide and hydrogen gas, I need to add 90.7 kilojoules. So what this means is that I can actually use this as a conversion factor. You know how much we love conversion factors in chemistry. So well, I can tell you that, say, for example, I can say a 1 mole of CH3OH is equivalent to 90.7 kilojoules of heat. Or, if and depending on what I need, I could also say that 90.7 kilojoules of heat is equivalent to 2 moles of hydrogen gas being produced. Does that make sense how I'm connecting the delta H to the molar amounts in the equation?
Yes, so we're just using it as a conversion factor.
Exactly. Now in this case, for part B, it asked us to calculate the amount of heat transferred when 45 grams of methanol is decomposed. So what I can do here is I can start with my 45 grams of CH3OH. So I'll go ahead and insert an equation. 45 grams, 45.0 grams of CH3OH. And then I can go ahead and multiply that times the conversion factor. Now, of course, I know that the delta H only relates to the molar amounts here, so what am I going to have to do for this first conversion?
Convert grams to moles.
Yes.
Absolutely. Very good. So I'm going to have to convert grams of CH3OH to moles of CH3OH.
By using the molar
And
mass.
exactly, I need the
Yes.
molar mass. So if I calculate the
32.0
molar mass, what do I get?
32.0 grams.
32.0 grams. That was fast. Yeah, 12 for 12 for the carbon,
I
and
cheated.
then each hydrogen is about 1, so that's 4. 12 for 4 is 16, plus 16 from the oxygen, that's 32. Very good. And then once I have moles of CH3OH, now I can go ahead and proceed to do another conversion factor and convert the moles to heat using my delta H. So what goes on the bottom here?
Moles.
Uh-huh.
Yes.
Moles of CH3OH. Now, it wouldn't necessarily be 1, but in this case, because the equation up here shows this as 1, I will put a 1 mole of CH3OH. Now, how many kilojoules of heat is equivalent to 1 mole of CH3OH being reacted?
90.7.
90.7. So in this case, essentially 90.7 kilojoules must be absorbed for every 1 mole reacted. And then all I have to do is multiply everything on top and divide by the bottom. And what do I get?
Does it need to be in joules instead of kilojoules? Or
No,
does it
it just says calculate the amount of heat transferred. Uh, Sometimes, I mean, unless it asks for a specific unit, like joules or kilojoules, you can usually just do it in either.
Okay.
It's going to be 128 kilojoules.
Uh-huh.
Yes.
128 kilojoules. And in this case, because there's only 3 significant figures in our starting value and 3 significant figures in each of our conversion factors, our answer will also be 3. Very good. Does that make sense? Easy peasy, right?
I wouldn't call it all bad, but sure.
All right. So now let's go ahead and do C. It says for a given sample of CH3OH, the enthalpy change is 18.5 kilojoules. How many grams of hydrogen gas are produced? In this case, we're kind of working things a little bit differently, aren't we? What are we going to end up having to start with here?
The 18.5 kilojoules.
18.5 kilojoules. Very good. And if we multiply that times our conversion factor. Okay. So I'll multiply that times our conversion factor. I know kilojoules has to come on the bottom so that it cancels. And what can I convert kilojoules to that will help me get to my desired answer?
Moles.
Moles of what?
CH3OH.
Well, I could convert to moles of CH3OH, but what am I trying to solve for here?
Oh, hydrogen.
Yeah, in this
Oh,
case,
so
so
2
I'm
moles of
looking for
hydrogen
moles of
to be on top.
hydrogen.
Yeah.
Yeah, I might go ahead
Yes.
and use hydrogen instead. Otherwise, I would end up adding an extra step. So how many moles of hydrogen gas is equal to how many kilojoules?
2. 2.
Yep, 2 moles of hydrogen, because the equation has a coefficient of 2. And how many kilojoules?
90.7.
90.7. Very good.
Wait, what
Now we
happened
have
to
the moles.
18.5?
18.5 is what we started with.
Oh, I'm sorry. Thank you.
Yeah, no problem. So now we just have to do one more conversion. And we need to convert to grams because it wants us to give us, it asks for grams of hydrogen gas. So I know that the moles of hydrogen is going to have to come down here, right?
Right.
And grams of hydrogen can come up here.
2.00.
Mm-hmm. Or, well, 2.02 if you have 366, but yeah. Sorry, the OCD is kicking in, I'm sorry. But 2.002 moles or grams of hydrogen for every 1 mole, or 2.016 if you do 4 sig figs. But now we're really, getting into some unnecessary decimal points. But anyway, so then you just multiply everything on top, divide by everything on bottom, and what do I get for my answer?
Zero point
2 grams.
0.22 grams? I don't think that's right.
0.822 grams.
Oh,
I get
0.8 there. Okay, that sounds better.
Yes. Yes.
I might not be able to do that in my head, but there's something fishy about 0.2. All right. There we go. Absolutely. So 2 down, 1 to go. Not too bad, right? Does it make sense?
Not too bad.
Now,
Yay.
B says, what is the value of the delta H for the reverse of the above reaction? In other words, if we flip that reaction around so that it's carbon monoxide and H2, what is the value of delta H?
Negative 90.7?
Yes.
Yeah. So it's kind of like if you look at back up those energy diagrams we looked at top. So like for example, the endergonic reaction, like the endothermic reaction that we deal with, this delta E here, this one right here, this delta E or delta H is positive 90.7. But if we were to go backwards, that means we're going to go from here back down to here. Well, that's the opposite. It's in the opposite direction, so that's going to be the opposite amount of energy. It's still the same energy transition. It's still the same difference in energy between reactants and products. It's just that if I was going forward with the reaction, I have to absorb energy to make it happen. But if since I'm going backwards now, if I was to do the reverse reaction, it would flip it to negative. So that's absolutely correct. So this is going to be a negative 90.7
Thank you,
kilojoules.
Elaine.
And then it says, and if that's the case, how many kilojoules of heat are released when 27 grams of carbon monoxide reacts completely with hydrogen to form CH3OH at constant pressure? So we're going to do one last little conversion.
Oh, I ran out of space.
So I'll take my 27 grams of CO. Do y'all want to try and take a stab at this yourselves, or do you want to kind of go through it together? What do you think? How confident do you feel?
I don't mind taking a stab.
All right, stab away. Not literally, please. I'm going to hide my screen so you can't see my work. When you have an answer, go ahead and raise your little hand. It's down by the whatchamacallit, the voice turning on and off thing. There it is. Yeah. Or if you give up, you can also raise your hand. And nobody will know that you don't have an answer. You just say, oh, wow, you're smart.
I already forgot what it was asking for.
It says if 20, how many grams or how many kilojoules of heat are released when 27 grams of CO reacts completely?
What is the relationship? How many moles are on the
You know
on
what?
the
Fine.
on the what?
Fine.
I'm sorry, I just needed that one number. You're good. That'll work. Thank you.
That's fine. I'm just not going to work on it.
Oh.
Yeah, you can just figure it out yourself.
Nice.
I did this. Well, I have the answer, I think. Oh, I'm sorry. I forgot to raise the hand.
Oh, there you go. Anybody else have an answer? How about you, Juan? Sochi? You got an answer? Do you think you are ready to rock this?
Drum roll.
No, I think I give up.
That's okay.
For it.
Yeah, that's okay. That's okay. Practice makes perfect. You'll get there. All right, so let's go ahead and take a look at it. All right, what is your answer, Ethan? And depending upon whether or not your
Well,
answers.
I love it when the pressure's on me. So how about negative? Right. Yes. I'm thinking negative 87.4 kilojoules. Does that sound right?
Yay!
That is a great answer. It's also wrong.
Oh.
It's wrong. But it's
Great
wrong
job.
for a really stupid. It's wrong for a really stupid reason.
Oh, wait a minute.
Because
Did you say?
What did I do wrong?
Huh? Did you say minus 87.4 is not the right answer?
it is not the right answer.
Is it because what?
And you are correct in using negative 87.4 for the conversion, or negative 90.7 for the conversion here. The reason it's not the right answer is because of semantics. That basically means useless wordplay. Even though technically speaking, when you do this calculation, the answer it gives you is negative 87.4 kilojoules. Technically, because of the wording of the problem, it says how many kilojoules of heat are released. Since it already says the heat is released.
That's funny.
If it asked you for what is the enthalpy change of this process, then the answer would be negative 87.4.
Dang.
But since it asked you how many kilojoules of heat are released, the negative indicates the fact that it's released, but you can't have a negative amount of heat released, so the actual answer is positive 87 kilojoules, 87.4
You fool
kilojoules.
me every time, sir.
I know. Shame on you. The reason I did that is not actually to be mean, although that was part of the reason. It was actually because it's because I've actually seen this on a number of professors' tests. They'll say how much heat is released, and they'll give both the positive and negative answers, but the negative answer is wrong. Because whenever it asks how much heat is released or how much heat is absorbed, the answer is always a positive number because you can't have a negative amount of heat absorbed and you can't have a negative amount of heat released. It's like saying, so like for example, it's like saying this. I can't have a negative number of people in this session, right? I can't go back to my boss and say, you know, yesterday at that review session, I had negative 3 people show up. So all I can say is, no, there's 5 people who showed up. So I can say that if he asked me how many people left if he asked me how many people left from the beginning to the end, well, I can say, well, 1 person left. okay? But I can't say negative one person left. One person left. However, if you ask me what was the change in the number of people who attended your session, he wouldn't ask me this because it's a ridiculous question. But what is the change in the number of people from start to finish, or from the beginning towards the end? I would say, oh, well, we had a change of -1 people because the final number of people was only 4, but the initial number of people attending the session was 5. So change can be negative. And change in delta H, therefore, can be negative. But heat itself, the amount of heat, can't be negative. Change in heat can be negative, but not the amount of heat itself. So it's a semantics thing. It's stupid. It's one of the things that drives me crazy about thermochemistry, but unfortunately it is what it is. So it's one of those tricky things where if you ever see them ask for how many kilojoules of heat, automatically know that the answer is going to be positive because it's not. If it doesn't say what is the change in heat or what is the enthalpy change, then it can't be negative. Does that make sense?
I'm just going to give you my brief opinion here. I've taught this course, and I would never do that to my students.
You're nicer than some professors. I have to confess, I actually probably would do this to my students just because I'm a sadist, but that is, just kidding.
that's, yeah, I mean, I can see why you would, but yeah, but okay.
Great
We just have to.
Why would I? No, I'm just kidding.
Questions are worded. Oh,
So what do you think, guys? Does that help? Does that make sense?
Yes.
Okay, good. Ethan, are you with me? You with me, buddy? I think I'm getting the cold shoulder.
Fun.
Oh my goodness. Okay. Oh my goodness. That's too funny.
Oh gosh, too funny.
Okay. So let's go ahead and move on. We'll look at number 4. Okay, so now it says, what is the enthalpy change for the reverse reaction? Oh, this is similar to the one we did before. What would the enthalpy change for the reverse reaction be? What do you think?
-630 kilojoules.
Yes.
That is correct, absolutely. And then it says, what is the delta H for the formation of 1 mole of acetylene?
Which one is acetylene? I can't read that close, I guess.
Oh, well, let me go ahead and zoom it in. One page. No, wait. My page. There we go.
Much better. Wow. Much better.
Yeah.
Woohoo.
So let's take. So I'm going to go ahead and. What is the enthalpy change for the reverse reaction? Well, first thing I'm going to do, I'm going to copy this because I'm lazy and I don't have to retype it. Then I'm going to go ahead and say, okay, well, the reverse reaction means that this is going to go over here, and this is going to go over here, and look how little work I had to do. And this is going to change this to a -630. Now for part B, it says, what is the delta H for the formation of 1 mole of acetylene? What is the delta H for the formation of 1 mole of acetylene? So if I only wanted, right now, acetylene is this guy. Okay? So acetylene is also this guy over here. So which equation would I use to describe this? What is the delta H for the formation of 1 mole of acetylene? Which equation am I going to actually reference here? Am I going to reference this first one or the second one?
Since it doesn't mention explicitly that it's going to be the reverse reaction, I'm going to say it's going to be the first reaction.
Well, explicitly, it actually tells you that this is about the formation of acetylene. Formation means that acetylene is a product.
Right.
So that means I definitely have to use the first one because acetylene is only a product in the first one. However, this is 3 moles of acetylene here. So what I can do here is I can actually use the same principles that I did last time. I can use the same principles I did last time. Ooh, stop growing. And I can insert an equation, and I'll do 1 mole of C2H2. I'll just do it like this. All right. And then from 1 mole of C2H2, I can then multiply this times the conversion factor to calculate what the enthalpy would be. If I only wanted to, because this enthalpy right here, this corresponds to the formation of 3 moles of acetylene. But if I want to only form 1 mole of acetylene, now of course I could do the obvious thing and just divide this by 3, but what would the fun in that be? So I'm going to go ahead and show it conversion factors, just because I can. There we go. And this will be 2 kilojoules. I want the enthalpy. So now this is actually a positive 630 kilojoules. That corresponds to 3 moles. Whoa, that's not right. 3 moles of acetylene. So then I can then say that the delta H for this process is simply going to be 210, positive 210 kilojoules. Now, this is actually an important principle that's pretty much intuitive, but it's a good to get in the habit of. You can actually multiply this equation, but if you do, if I multiply this equation by 2, in other words, if I put a 2 in front of C6H6 and multiply the 3 by 2 to give us 6, I multiply this equation by 2, then I multiply the delta H by 2. If I multiply it by 5, then I multiply the delta H by 5. If I divide it by 3, as I did here, I divide the delta H by 3. Does that make sense?
So why would it not stay proportional since you're still making 3 moles of acetylene to 1 mole of benzene? Why would the delta H change in the quantity that you're making? Because of the larger area that you're putting it into, or what?
Well, the delta H, well, think about it this way. If you wanted to boil a cup of water, it's going to require a certain amount of heat. If you want to boil 3 cups of water, you're going to have to add 3 times as much heat to make it boil because there's more of the substance to heat up.
Yeah, that makes sense. Yeah, it does.
So, and likewise with chemical reactions, and let's think about it like in terms of, like, say, for example, a heat pack, right, or a cold pack. If I want, if I have, want a certain amount of heat, then I crack 1 heat pack. But if I want twice as much heat, I'm going to crack 2 heat packs, and that's going to give me twice as much heat. So essentially, the amount of heat transferred in a reaction is directly dependent upon the amount of reactant that's actually reacting. The more reactant that you have, the more heat is absorbed or released. So I don't know if that kind of clarifies things, but I think that kind of.
Yeah, it did make sense. Yeah, that was.
And it says, which is more likely to be thermodynamically favored, the forward reaction or the reverse reaction?
What does that mean, thermodynamically favored?
Thermodynamically favored. In other words, which one is more likely to happen? Which one does the delta H indicate is going to be more probable? Because think about it this way: if we go back up to our original energy diagram,
Yes.
is it easier to, like, if you think of this as like a sled, okay, is it easier to go down the hill or is it easier to go up the hill?
Down.
Yeah, it's always easier to go down, right? It's always easier to go from a point of high energy to a point of low energy. And that's true with gravitational energy in the form of a sled, and it's also true in terms of chemical energy, chemical potential energy. It's always easier to go downhill, to go from a high energy point to a low energy point. So
Yeah,
in
I
other
mean,
words,
it's probably better to describe it as not necessarily going downhill because you're going downhill in both cases, but the potential energy barrier that you have to overcome is the key there. So in the first reaction profile, you see that it's got a shorter energy, it's got a shorter activation energy, potential energy barrier that you have to overcome. It's easier to climb that small hill rather than to climb the larger hill. Does that make sense?
well, I mean, the point here, when it comes to thermodynamically favored, you're basically looking at what's going to give you the more stable product. Okay. The fact that the delta H for this one is negative 630 means that the product is much more stable than the reactants. To go from 3 acetylene molecules to 1 benzene molecule, that releases 630 kilojoules of heat, which means that these 3 acetylene molecules have 630 kilojoules of heat more, or 630 kilojoules more potential energy than the C6H6. So this is very high energy and it's going to a relatively low energy molecule. And in the process, a lot of excess energy, a lot of excess heat is released. So anytime you go from a high energy molecule to a low energy molecule, that is what's considered thermodynamically favored. There's another topic which is refers to as kinetic favorability, and that has to deal with activation energy, but we're not going to really talk about that in Gen Chem 1, and honestly not too much even in Gen Chem 2, although we will do a little bit in rate. But the bottom line here is when it talks about thermodynamically favored, it just means which one gives you the more stable product. If I'm adding 630 kilojoules of heat to make the product, is that product higher energy or lower energy than the reactant? What do you think?
Say it again, please.
If I'm adding 600, and this is also another thing to keep in mind, when the delta H is positive, that means reaction's absorbing heat, which effectively means that heat is a reactant. Okay? It effectively means heat is a reactant. So, and then when delta H is negative, it actually effectively means that heat is a product, it's released. Okay? So, based on this, which one is the lower energy substance? Acetylene, CH2, C2H2, or the C6H6? Which is lower energy?
The C6H6.
Yeah, the C6H6 is lower energy because I have to add a whole boatload of energy to turn the C6H6 into C2H2. So these 3 acetylene molecules are extremely much more energetic than the C6H6. They have much more energy. And thermodynamically favored means you're favoring a more stable product, a lower energy product. And so in that case, which one is more stable, which one's lower energy? As you said, it's the C6H6. So that means this reaction, the reverse reaction, is going to be thermodynamically favored. Does that make sense?
Yeah.
Basically, anytime delta H is negative, the products are thermodynamically favored. To give the Cliff Notes version.
Because it has a lower energy state than its alternative, the positive. So if it sits at a lower energy state, it's more stable, it's thermodynamically favored.
Mm-hmm. Any questions on that? Does that make sense? We all good?
So far, so good.
So far, so good. Okay, good. All right, so that brings us to D. So we established there was the reverse reaction here. Here's the more stable, here's the more favored. Now we go, if C6H6 gas were consumed instead of C6H6 liquid, would you expect the magnitude of delta H to increase, decrease, or stay the same? What do you think?
Increase.
I think that wait a second, are they not just the same? Oh, this gas, I'm sorry. That's funny. I would assume the amount of energy necessary would be less than, because it's easier to move a gas around than it is a liquid.
Yes.
Well, that's not wrong, but there's a simpler way to think about it. What's a higher energy state of matter, gas or liquid?
Gas.
Yeah. So if we're looking at this reaction, this is an endothermic reaction to go from C6H6 to C2H2. So if the original, let's say the original energy diagram looks like this, right? The original energy diagram looks like this. Here's your liquid benzene, and here's your C2H2.
We can call
As a
that
gas, because a gas has a higher energy to start with, the gas has a higher energy to start with, your reactant is now right here. And it still goes through the same process here, but it starts out at a higher energy state. So with the magnitude of delta H, remember the delta H here is the difference between here and here. Here's your delta H. Here's your delta H of the reaction for the liquid. And here, this is the delta H for the gas. What happens to the magnitude of the delta H? Does it increase, decrease, or stay the same?
It looks like it decreases.
Yeah, it decreases.
So
If
you
you
got it
start
right.
from a higher energy point of view, it's pretty easy to
Yes.
see that start from a higher energy point of view, it's going to be less of a difference between the product and the reactant in an endergonic reaction or endothermic reaction. Look at this as delta H. Does that make sense?
I don't really
Gas
get
is a
this
higher
one.
energy phase of matter than liquid, so it pushes that initial state higher, and therefore final minus initial ends up being a smaller number.
So, Professor Depo, what did you mean that it's not entirely correct?
What's not entirely correct?
Oh, no, maybe I misunderstood. Okay.
You say his
No,
answer
maybe
was entirely correct.
Oh, he said just gas. Well, he said gases can move around more freely, and that's true, but that's not necessarily the main point. The main point is the fact that a gas is higher energy than a liquid, and therefore, since it already has more energy to begin with, that's going to actually cause the difference in energies to be smaller because it's going to a higher energy. Now, interestingly enough, if this question was reversed, in other words, if we were looking at the reverse equation, and let's say that this was going from the C2H2, let's say this was a C2H2 here, right? If we were saying this is C2H2 and we were saying, well, what about if the C2H2 is a gas? Well, if the C2H2 is a gas, then that would put the C2H2 up here. Well, I guess it is a gas. Never mind. Bad analogy. But effectively, if this was the idea is if this was an if this was an exothermic instead of an endothermic reaction, having the higher energy reactant would actually cause the delta H to be larger if it was exothermic. Because if it was exothermic, then that means that this would go, the final state would be less. And therefore,
Yes.
for an exothermic delta H, the liquid delta H would be less than the gaseous delta H. Does that make sense?
Yes.
What if you factor in pressure with the gas?
Constant pressure. Don't talk to me.
Oh, okay. All right.
No, just kidding. we're not dealing with pressure. Stop making it complicated.
I understand.
It's already
I gotcha.
chemistry. It's already complicated enough. No, no, it's a good question. Factoring in pressure would open a whole new can of worms, and I don't think we want to deal with that right now. But kudos to you for having the intellectual interest and wanting to delve into it. But at this point,
Well, thank you.
it's also 8 o'clock, and I don't feel like going into it. All right. Well, I sadly have to say that we did not get through a bunch of things that I really wanted to get through. But that's actually not to be unexpected, because there is a lot that comes along with thermochemistry. So since most people are doing gases next week, I'm going to go ahead and jump into gases and the gas laws next week. But right after that, we're going to go ahead and hit quantum theory hit it running. Does that sound like a plan? What do you guys think?
Yes, sir. That sounds great.
But I will post thermochemistry part 2 on our website under the main thing. And that will be under not the archives, but the main page. You go to 1411, workshops and events, CHEM 1411, scroll to the bottom. I'll post the 13 chemistry video, this one that we just did. And I'll put thermochemistry part 2, I'll post that. And so you can watch it at your leisure. Anyway, I hope that helps. But thank you all for coming. It was a lot of fun. It was a fun session.
Thank you.
Yes.
You're welcome. All right, I'm going to go ahead and stop recording now. Have a great night. Come next week.